I want to welcome everybody again. This is She Has the Floor, the inaugural event for October 5. This is a collaboration of JILA, which in 1962 came into the world as the Joint Institute for Laboratory Astrophysics at the University of Colorado Boulder. Our other partners for this event are the JILA Excellence and Diversity and Inclusivity group at the University of Colorado Boulder and Pretty Brainy. I am Heidi Olinger. I am humbled and honored to be the founder and chief executive of Pretty Brainy. And I would like to now introduce Gail Geschwind, who is on the team at JILA. She is doing her graduate work in physics at CU Boulder, and she is a co-founder of the Excellence in Diversity and Inclusivity Committee at JILA. Gail does single molecule biophysics research at CU Boulder with Thomas Perkins. She received her Bachelor of Science degree in physics and math at Stony Brook University, New York. She loves to participate in outreach programs of all kinds, including JEDI, a group that she helped to found, as I also already mentioned, but it's worth repeating. And she loves to help promote diversity as an integral element of collaborative research. Gail.
Hi, everyone. It's great to see so many people here. As Heidi said, I'm Gail. I'm a graduate student, and basically you can think of it like I'm in 21st grade. So, I went to high school, I finished 12th grade, I went to college, and then I just didn't stop. So now I'm in 21st grade. So I study biophysics. Basically, I look at single pieces of DNA, which is what makes you who you are, and see how they bend if I pull on them really hard. And I work at JILA, which is a collaboration between CU Boulder, which is the college I go to, and the National Institute of Standards and Technology, which is a government lab. And there is so much really cool and diverse research happening there. We have people looking at astrophysics things. We have people studying lasers and all the cool things that they can do. People looking at atoms and molecules, and even people making the most precise clocks in the entire world. And as Heidi said, I'm also involved in an organization called JEDI, and we work on making sure that we have a diverse environment at JILA and helping promote diversity in STEM overall. And that includes making sure that we get more girls like you interested in science. So one of our most important messages is that science is for everyone, and I hope that you take that to heart. And I know that you're going to love today's talk, but before we get to that, I'm going to turn it back over to Heidi.
I want to give a big shout out today also to another member of JILA and JEDI, and that's Kenna Castleberry, who gave us the spark to do this event. She brought together Pretty Brainy and JILA and JEDI, and we can all thank Kenna for the fact that we're here and gathered and about to have a great science experience. So Kenna, just give everybody a little wave if you can. So let's give sparkles for Kenna. So just kind of, yes, okay, fabulous. Thank you very much. All right, I also want to thank the people who helped make Pretty Brainy possible. And the list includes the Deaver Phoenix Foundation, HP, the Community First Foundation, Jane Hamburger, Marianne Heyman, Toolbox Creative, the Women in Science Network at Colorado State University, and many other people in the community just like you. Our co-host today is Isabella B. Petner. She was named B by her sister because of all the busy things that she did when she was young. And just briefly, I will tell you that I first met B when she was just finishing 6th grade in 2012 and beginning to develop her passion for science, tech, engineering, art, and math. She had such a huge passion for math that she graduated with an associate's degree in math at only age 15. Engineering was her first, I think, major that she declared when she started college. And from engineering, though, she radically shifted her direction to fashion design. It was a passion of hers since the time she was little, and something that I can humbly say Pretty Brainy helped her affirm through the different STEM of fashion design programs that we had brought to the community. She graduated from Colorado State with a bachelor's degree in apparel design in 2020 and was recognized as that class's outstanding graduate. She's now an assistant sweater designer at Kohl's in Wisconsin and pursuing her passion of fashion design while bringing in the science and the math that she also loves and being pretty brainy. So, Bea, thank you so much for co-hosting.
Thank you so much. Thank you so much, Heidi, and I am so excited to be here and to see all of you, and I'm very excited to introduce Dr. Anne-Marie Madigan, who is a theoretical astrophysicist. She was born in Dublin and was one of the first students in Ireland to receive an undergraduate degree in astronomy. She received this degree from the University of Ireland in Galway. She then received her PhD in astronomy from Leiden University in the Netherlands and was a NASA Einstein postdoctoral fellow at the University of California, Berkeley. Since 2016, she's been an assistant professor in the Astrophysical and Planetary Sciences Department at the University of Colorado in Boulder. And currently, she is a theoretical astrophysicist who explores the dynamic of stars and gases around supermassive black holes, dark matter in galaxies, and the icy worlds of the outer solar system. So I'm so excited to pass it off to Dr. Madigan to tell you all about her wonderful things.
Wonderful. Okay, thank you so much, everybody. And I'm really excited to be here today to get to talk to you. I, as Bea said, I'm an astrophysicist, and in particular, I'm a dynamicist. So what that means is I get to work on the motions of bodies in space. And so I have three particular areas that I work on, and I have a great group in Boulder who help me. So the first one on the largest scales is that of galaxies. So galaxies are collections of billions of stars all together, working together, and they produce these amazing spirally features if they're in disk galaxies. And I'm really interested in dark matter in these galaxies. So it's not the focus of the talk, but I'll just let you know, most of the matter in the universe is dark in the sense that we cannot see it. We only know it's there because it gravitationally pulls on the stuff we can see. So that's something that we're really interested in my group in Boulder. The other thing that's wonderful to work on are the motions of stars and gas around supermassive black holes in the centers of galaxies. And again, that's not the focus of this talk, but supermassive black holes are super. And so if anybody is interested in these, you can always ask me questions about this stuff at the end. You don't have to stick to the third topic that I will be talking about today. And that is all about the odd things that are going on in our outer solar system. So what I'm showing you here on the right-hand side is actually this gorgeous image of Pluto in our outer solar system that was taken by a spacecraft called New Horizons very recently. As it I don't know what you would call it, but it zoomed, if spacecraft zoom, as it zoomed past the dwarf planet, that's what we call this, a few years ago. Okay, so we're going to be focusing on this talk on our outer solar system and the strange things that are happening out there. So I want to start off with what do I mean by outer solar system? What is that? So the solar system is the region of space where bodies that could be asteroids or comets or planets are all in orbit around the sun. And so this is our inner solar system, the schematic. And we have the orbits drawn out of Mercury, Venus, Earth, and Mars in orbit by the sun at the center. And then we have something called the asteroid belt. So these are really, really small, mostly rocky little bodies. They're not big enough to be planets. There's loads of them. And then further outside, we have Jupiter that moves on this orange orbit. So that's not the end of the solar system. We've still got a few more planets left, but we have to zoom out. And so what you're seeing here is the outer solar system. So you got this Jupiter in orange, then Saturn, Uranus, and Neptune at the end here in blue. Okay, I'm also showing the orbit of Pluto, but again, Pluto is not a planet. It's too small. And in fact, Pluto is actually just one of many bodies in the outer solar system. And it's called the Kuiper belt. So these bodies that are not big enough to be planets, but there's a lot of them. And we've been discovering more and more and more as the years pass. It's really hard to see out there because all of these bodies, they don't shine. They're not stars, these rocky, icy bodies. So we only see them because the sun shines light to them. It reflects off their surface, and then a tiny amount hits our telescopes back on Earth. So they're really small, really hard to detect. But what I'm really interested in is everything outside of this. And for a long time, we didn't think there was anything outside of this in our solar system. We knew there were like other stars, other galaxies, black holes, but we just thought that's it for our solar system. This is the edge. There's nothing else. And we were wrong. So you see there's a body on the top right-hand corner here that's called Sedna, this little red dot. So you might think if Sedna is part of our solar system, it's going to have this orbit. It's going to have this motion around the sun that looks very much like Pluto, for example, or a Neptune. So now I'm going to show you what Sedna looks like. So this is the orbit of Sedna. Sedna takes over 10,000 years to go once around the sun. That's in the same time the Earth goes once around the sun. It takes 10,000 years. So this is pretty extreme. Okay, and so we're going to be focusing on the small bodies just like Sedna. So I'll call them Sednas. You might want to ask, what does this look like? What is this Sedna? This is an artist's impression of Sedna. So we have this body, it looks reddish, a bit like Pluto. We think it's extremely cold, like very, very icy. And this, I don't know if you can see my cursor, but if you see a little shining dot to the right of the image, this is what the sun would look like at daylight from Sedna, because Sedna is so far away from the sun. This is the brightest it would ever seem. It just looks like another star because it's so far away from the sun, but it still is in our solar system. Now, this is an artist impression. The best telescope we have, not even in the world, it's in space. That's a Hubble Space Telescope. This is the best picture it's ever taken of Sedna. Just a little sad. That's the best we can do because it is so far away. So we don't have a good picture of what Sedna looks like. There's no spacecraft out there to take a better photo of it. But what we do know about Sedna, because we've been tracking it as it moves very slowly across the sky, is we know its orbit really well. What is the path it takes around the sun? We've only seen it move a little bit along that orbit because it takes 10,000 years and we haven't been looking at it for 10,000 years, but we do know its orbit really well. That's Sedna's orbit. But if we actually take all the Sednas we see out there, I've just introduced one of them to you, they're doing something odd. And then that's in addition to the fact that they take 10,000 years to go around the sun. And so I'm going to show you schematically what I mean by something is odd about their orbits. So ignore the orange line for the moment. What we see here all on the left-hand side of the image are different Sedna type bodies. Here in particular is the orbit of Sedna as it moves around the sun. So it's a collection of bodies that we've seen in the outer solar system. And obviously what's odd about them is that they're not just anywhere in orbit around the sun. All of the orbits are pointing in the same direction. They're all clustered onto one part of the sky. So we have Sedna. We also have my favorite. This has a not such an interesting name of 2012 VP113. It was discovered in 2012. That's where the first digits come from. But because Biden was vice president in 2012, or VP, it has a nickname Biden. That's what all astronomers call it. But it's just like a Sedna, very similar orbit and pointing in the same part of the sky. So what is going on? Why are they all doing this? Well, I've taken this image from a press release in 2016, where astronomers, Madigan and Brown, have suggested that there could be a new planet in our outer solar system. And because this would be the 9th planet in our outer solar system after Neptune, they called it Planet 9. And so if this planet is really, really big, it'd have to be like 6 times the mass or the size of Earth, and it has just the right orbit, it can shove all the orbits of the little Sednas onto the other part of the sky. And so all around the world and using telescopes in space, people are trying to find Planet 9. And they've been doing this since 2016. So using the Hubble Space Telescope, using Subaru, which is an amazing camera in Hawaii, using telescopes in Chile, and also using archival data. So that's data that's already been taken, surveys of the sky, but nobody was looking for a new planet before. So they're combing through it, trying to find it. And I think they're looking for the wrong thing. So this is what I've been working on in my group. So I'm asking the question, do you actually need a Planet 9? So in my group, we work on the collective gravity of billions of small bodies. And we ask, what structures are they forming? And so this is not new. When we look at galaxies, like this, the image of a galaxy I showed you on the first slide, we can see this kind of like elongated feature. We call them bars. And then these beautiful spiral arms, they're spiraling outwards from the center. There is no Planet 9. There is no equivalent of this huge massive object in this galaxy. What is causing this barred feature and these beautiful spiral arms is just the collective gravity of billions of stars working together. And so we see this all over the sky with good telescopes. It's hard to see galaxies with your naked eye, but we see them all over the sky, and we know it's just the collective gravity of billions of stars. So we're asking the question, if comets and asteroids and these small Sednas actually shone like stars, what type of structures would they be forming? And we don't know because it's really hard to see them. So we're only just now detecting them in the outer solar system. So what we use are computer simulations. And so into our computer simulation at CU Boulder, and we run them on a supercomputer, so they take a long time to run, we put lots and lots of these Sednas. We put them in where we see them, and then we let them interact gravitationally in our computer simulation, and we see what type of structures are they forming. So I'm just gonna, this is the only kind of sciencey slide in the sense that these are real results from the supercomputer. So we see here on the left-hand side of the screen, we are looking at what we call the surface density, or just how many objects do we see at one point in the simulation. And so yellow means we see lots and lots of bodies. And the top panel is like, we're looking just straight down onto the solar system, and we're looking at all of those Sednas. Okay? And then the bottom panel is like, let's say we're looking edge onto the system, and we can see all of those Sednas. And so we run it in our computer. They all gravitationally interact with each other, just like they were stars in a galaxy, except now they're in orbit about the sun. We see some really interesting things happen. So instead of them interacting with each other and kind of puffing out and making a thicker disk, they do this with the orbits. Oh, let's see if you can see my hands. They go like this, whoosh, like this. The noise is very important. That doesn't come out of the computer though. That's added effects. And then you can see really interesting things start to happen in the top panels, like the orbits kind of shrink a little bit. And then the orbits go whoosh, like this, and go right back down. And then in the final plot, you'll see yellow shows like where most of the Sednas are. See in that top right plot, the yellow isn't just a full circle. And what that means, like there's more particles or more Sednas on one, on the bottom part of the plot than the other. What that means is that their orbits are beginning to cluster together, kind of like you have orbits, and instead of them being scattered all around the sky, they kind of want to align. And so what we're finding, this is from our press release last year, is that we can actually reproduce what we're seeing in the outer solar system just with the collective gravity of all these Sednas working together. So we have the sun here, and then orbits collecting together, again, some artist's impression. And they're all doing it by themselves. We don't actually need a new planet in the outer solar system. But we do not get everything for free, okay? So our predictions are, we don't need a new planet in our outer solar system, but we do need a lot of Sednas out there. this stuff doesn't happen unless you have a lot of them out there. More than combined together would make up the mass of the Earth. Actually, about 10 or 20 times more the mass of the Earth, all distributed in these small little bodies. And so just like there's an asteroid belt in our solar system, and there's a Kuiper belt in our solar system, this would be a new belt in the very outer solar system that we're just beginning to see. And we're going to find out if it's really there or not, and if there's a planet 9 or not, when the new telescope comes online. That's what we say when the telescope starts opening up its dome and taking light. And this telescope is called the Vera Rubin Observatory. And I love this name because Vera Rubin is one of the discoverers of dark matter. So it's kind of a nice loop happening in the research that I'm interested in. And so this observatory, when it opens up and starts taking survey of the sky, it will find out if there's a planet 9, and it will also find out if there's this new massive belt in our outer solar system of material. And so we're actually working with the team on a survey simulator where they take the results of our simulations and they say, Vera Rubin Observatory will be able to see this or it will not. And they can even adjust how they actually map out the sky to best try and find it, or to say it's actually not there, you're all wrong. But that's okay. That's science. It's okay to be changing your theories as new data comes in and see what works best. And the next thing that we're thinking of is, if this belt is there in the outer solar system, I have these words here, high inclination. What I mean by that is that there's a plane of the solar system where all the planets are. This belt would actually be very high inclination. It would kind of leap off the plane. So there'll be lots of bodies high off the plane of the solar system. And those bodies will very occasionally pass in front of a star. And that's what's called a stellar occultation. So that's another way to put constraints on this belt in the outer solar system. If we take surveys of looking at stars, every now and again, we're going to see one of these bodies pass in front of a star. And we're going to be able to know that it was a body from this belt, a little Sedna. So, okay, that's what I wanted to talk to you about today. So thank you to everybody for coming. And once again, you can ask me questions about any of this. I think it would be really exciting. And now I'm going to turn it over to Bea. I'll keep my screen sharing for the moment, but maybe when we ask questions, I'll turn it off. Thank you.
Thank you so much. That was so interesting. Before jumping into questions, I'm just going to go over some quick guidelines. So please place your questions in the chat function, and then Heidi and I will call on you to pose your question. Please definitely take part. Ask questions. Every question, as Heidi said earlier, is a good question. And then when we call on you, say your name, where you're from, and as appropriate, your grade level. So we're seeing some questions start to pop in. So I'm just going to start with Sophia, the first question in the chat. If you want to unmute yourself, introduce yourself, and then ask your question.
Hi, I'm Sophia McDonald. I'm from Fort Collins, and I'm in 6th grade. I was wondering, like, why does the orbit of the Sednas change?
Okay, thank you so much, Sophia. That's a really, really good question, and that's what I spend most of my time working on. So the short answer for that is, let's see, I'm actually going to give you the proper answer. Okay, exactly what is going on is that you've got these Sednas in orbit about the sun, and they're very small, right? So you might think, well, their gravity is very weak. But the thing is, their orbits don't change that much. Just like the Earth going around the sun, the Earth goes around the sun, and a year later, we land back in the same place. We don't just like travel off into outer space, right? We do the same orbit again and again and again. So these orbits of Sednas, they do the same thing again and again and again for a really, really long time. So even though they're very small, they are exerting a gravitational force on nearby Sednas that builds up and up and up and becomes really, really strong because it's always the same orbit after orbit. And those gravitational forces between the orbits actually cause the changes. But it's complicated physics, but that's like the basic idea. But it's a great question because that's the whole thing you want to do, right? You get a result and you want to go, why? Why are you doing what you're doing? And it's new. People didn't realize they would do this.
Claire Denny, would you please introduce yourself and ask your question?
Hi, I'm Claire Denny. I'm in 8th grade and I'm from Fort Collins. So my question is, if there is a planet 9, could that like impact our lives like bigly, or like what would happen if there is a planet 9?
Yeah, thanks, Claire. So the real answer is no. Like, not really. So the planets we know of in our solar system, they're all relatively close to the sun, and we can see a lot of them in the night sky. If we know where we're looking, you might have seen Jupiter and Saturn. Uranus and Neptune are much harder to see, but you can sometimes see Mars and Venus, for example. Planet 9, if it exists, is so far away, there is no way you will be able to see it in the night sky. And this is why it hasn't been discovered. If it does exist, we're going to have to use the best telescopes that aren't even built yet to try and see it. And so it's so far away, it's not going to make much of a difference. I think what will change are textbooks. Our textbooks will all be like, we have 9 planets, and it will be called something official. I don't think its official name would be Planet 9 for all time. And then for astronomers, for people who work on outer space, it will be really interesting to try and understand, how did the planet get there? So we understand how the planets that we know of in our solar system formed. They formed in a disk of gas and dust. But planet 9 is so far away from the sun, it shouldn't have formed there. And so if it exists, we're going to be like, we have a lot of work to do because we do not understand how it got there.
Thank you.
Thanks for the question.
Awesome. And then I'm seeing some similar questions pop in. So I'm going to pass it to Althea to ask hers, and then hop to the other question after that.
Hi, I'm Althea Todd, and I'm in 6th grade. And I'm wondering, what is a supermassive black hole?
I'm glad you asked. Supermassive black holes are the best. So first of all, black holes, just in case anybody isn't too familiar with black holes, I don't know why a lot of people would be walking around being familiar with black holes. So let me explain what they are. A way I think that is intuitive to understand is that if you try and jump off the Earth, you are not going to get off the Earth. I don't know if you've tried, but to jump off the Earth, you need to reach what's called, good, I see Sophia is attempting it. Thank you. Science in action. You're not going to do it because to jump off the Earth, you need to reach what's called the escape speed. And I'm European, so I'm going to tell you it's 11 kilometers per second, and whatever that converts to miles. Very, very fast. Kilometers per second. So you're not going to do it in a car if your car could travel upwards either. This is why we use rockets and a lot of rocket fuel if we want to get into outer space. Okay, so knowing that planets have an escape speed and Earth is 11 kilometers per second, if a body is smaller like the moon and has less gravity, thank you, Gail. Yes, it's very fast. A body like a moon, because that has a smaller gravity, you don't need to go as fast. A body like the sun, you have to go something like 400 kilometers per second. If you were, for some foolish reason, standing on the surface of the sun, that's how fast you'd need to go in your rocket to get off the sun. Very, very fast. But you can imagine that there is a body, I'm not going to say it's a planet or a star, it's just something in space. It has an escape speed that's so high that nothing can get off its surface. not even light. The light has a set speed. And so if you have something that's gravity is so strong that not even light can get off its surface, and these exist, that means when we look towards the body, no light is coming from it, so we can't see it. That's a black hole. And so there's lots more cool things about black holes, but that's kind of how you could understand it. Somebody in space, so much gravity, nothing can get out of it, which also means if you get too close and you fall in, you're not coming out. A supermassive black hole is a really big one. And I mean really big. So we have the mass of the sun, and the mass, you can just think of like how much stuff there is of the sun. And the supermassive black hole in the center of our galaxy is 4 million times the mass of the sun. It's fantastic. And we know it's there, even though we cannot see it. You might be like, if you can't see it, like, why do you think it's even there? We know it's there because we can see stars orbiting around it, just like planets move around our sun. And just like we know how much stuff is in our sun because of these orbits, and we have mathematical equations that tell us, like, if you're orbiting like this is how much stuff you're orbiting around, and that's the sun. We're able to look at those orbits of stars and say, that's a lot of mass where we don't see anything. And it's a supermassive black hole. We actually see supermassive black holes in the centers of pretty much every galaxy. And we don't know how they formed. We don't know how they got there. Lots of cool mysteries. Thanks for the question. I love supermassive black holes.
Hannah, you have a question about being a scientist.
Yeah. Hi, Anne-Marie.
Hi.
My question is more broad and less about astrophysics, but I was just curious, being a female scientist yourself, what sort of advice you might give to somebody who is just starting out or who is thinking about becoming a scientist?
Thank you. That's a really good question. There's so much to say. The main thing is do it. Like, if you're interested in physics or astronomy and math and things like that, art, and like science is very creative. So I include art in that category. Absolutely go for it, because this is my job. I get paid to do this, and it's fantastic. It's a really good job. And computers are now really important for the job. Like, about 50 years ago, somebody with my job would be sitting in front of a lot of paper. Sorry, here's my notebook. A paper and a pen, and I still do that. But these days, computers are so powerful that we all use them to do, for example, these simulations. Like, what do like small little bodies in the outer solar system, what do they do when they gravitationally interact with each other? That we use computer simulations for that now. So coding is really good. Just trying to learn how to code. I think that would be really useful. And events like these are really good. It's always good to have people who you can ask questions to, who can be your mentors, to just like watch out in particular for other women who can help you. And there's always women out there who can help you. So I think that's what I would say to that question, but it's such a big question. It's like, yeah, there's lots more. But yeah, if you're interested in this stuff, you should totally go for it, because it's really good fun and you get paid to do what you love.
Thank you, Anne.
Next, I'm going to pass it to Sophie to ask your question.
Okay, yeah, I had 2 questions. Are sednas, are they more similar in size to asteroids or dwarf planets, or somewhere in between?
Yeah, that's a fun question. So how do we know what size something is? That gets tricky. So the reason we know what size or like what mass bodies are in the outer solar system in particular is if they have a moon moving around them, because then we plot the orbit of a moon using those equations that I haven't explained, but I've told you exist. Then we can figure out what is the moon orbiting and be like, that's the mass and that's the size of the body. So we don't, so for bodies in the outer solar system like Sedna, they're so far away, we can't actually resolve a moon. So it's really hard. You have to make guesses. You have to say, I imagine it's made of some ice. I imagine it's at this, well, I know it's at this distance. And so this ice will reflect this much light. So it's going to be this size. So there's a lot of error bars in all our guesses. Okay, so that's kind of the boring way of answering. What we think it is kind of like the size of Pluto. And then you might be like, what's Pluto? What's the size of Pluto? Pluto is a little smaller than our own moon. So these are small things that we're finding out there. There could be much bigger stuff out there, but maybe at a further distance. And it's just going to take us more observatories and more telescope time to actually find those ones. They're further away. So yeah, think of them as like moon-sized bodies. You know, an interesting fact is that if you took the moon and you just put it somewhere else, you put it not in orbit around Earth, but you put it closer to the sun, made it orbit around the sun, we'd call that a planet. The moon is small, but it's still, you know, we call it a moon just because it's in orbit around a planet. It would be in its own planet, the poor moon, if it wasn't in orbit around Earth.
And Sophie, you have a second question, yes?
Yeah, so I remember that a few years ago, there was like this first photo of a black hole or something, right? Do you know which or where that black hole was?
Yeah. So there's a telescope called the Event Horizon Telescope that you may have heard of. It's kind of a really cool name. The Event Horizon is basically like the surface of a black hole. And if you go past it, you cannot get back out. You just can't. No matter how much fuel you have, you will never get out of this thing. So the Event Horizon Telescope is actually a whole system of telescopes around the world. And they have been looking at the black hole in our galaxy, but also in a much bigger galaxy. So it's further away from us. But the supermassive black hole there is about 1 billion times the mass of our sun. So it's really, really big. And it's got this huge disk of gas around it. And so what they've been doing is actually getting such a great photo of this area with such high resolution that you can actually see the surface of the black hole. It's completely black in the inside. And then you just see like the gas disk around it, which is really nice. And I say photo, it's actually not invisible light that our eyes see and we look at photos and we see. It's actually in radio, and we don't see in radio. Otherwise, it would be a very confusing picture around us. But it's a radio telescope, and they're able to then convert that to a visual image that we can see.
That is all so fascinating. Wow. I don't see any other questions, so I just want to open it up. If there's any other questions anyone has, to feel free to ask.
How do we know that the universe expands way further than just our solar system?
Great question. So we know that, oh wow, how do I even answer this? This is a great question. Yeah, how do we know that the universe is expanding is one question. How do we know that there's stuff beyond our solar system is another question. Right, so it's like huge questions, huge, really kind of fundamental questions in astronomy, right? You see something in the sky and you're like, I don't know where that is. Is that like near the next planet, or is that 1 billion, million, gazillion miles away, right? Like, how do you even know? So these are like tough questions, and we work on this a lot in astronomy. So one way we know that things are extremely far away is that, how to explain this simply, when we look at the light coming from like a star or a galaxy, we take what's called a spectrum. And a spectrum tells us like what made up this light. Is this light composed of like hydrogen or helium or all of these different elements? And it also tells us how fast is that stuff moving relative to us. And because we know the universe is expanding, so I might have to explain why do we know the universe is expanding, but because we know the universe is expanding, we know that things at a certain distance are moving this fast away from us. So if we look at that light, we take its spectrum, we're able to be like, oh, it's traveling really fast. That is really far away from us. There are other ways as well to figure out. One is called parallax, but you know, this stuff might take me a little longer. But if you can look out your window and see like a mountain or something like that, and you can like get in a car or run really fast, and there's a tree close. Oh, what am I doing here? Okay, look out your window. Let's say you're all looking at exactly what I'm looking at. Okay, you look out your window. There's a tree in front of you and a mountain in the background, and you go from. If I go too far, you won't be able to see me. I'm kind of like a haunty ghost. But if you go from one side of looking at the tree and the mountain, the tree will appear at a certain point in front of the mountain, and then you like run in a car, you run in a car, you don't run in a car, run or drive in a car and look at it from another angle. The tree might appear to be slightly in a different position with respect to the mountain. This is a terribly long, boring explanation, but you should do this experiment, okay? Just like look and see like, where's the tree with respect to the mountain if I look from different angles. We can do that for stars in the sky as the Earth moves around the sun. We can be like, okay, it's June and I look at a star and it's somewhere on the sky. And then 6 months later, whatever that is, December-ish, I look at the same star in the sky and it will appear to have moved a little bit against the background. And that's one way we can say like, where are things? Because we know the tree is in front of us or in front of the mountain. Again, a terribly boring, confusing explanation, but you're asking great questions. Distance in astronomy is really tough because all we have, first of all, is just like the sky and everything appears to just be like two-dimensional until you like really figure out these tricks for figuring out how far away things are. And things are really far away, mostly.
Hi, Anne-Marie. I know you talked about simulations, but I was curious if you could talk a little bit about what your day-to-day looks like as a theoretical physicist.
Yes, of course. So let's see, I'll give you an example of tomorrow. What am I doing tomorrow? First of all, I'm going to get set up at about 6 a.m. because I have a 2-year-old, and my 2-year-old called Emmy will want to talk about owls. So we will spend the first part of our day discussing owls, maybe foxes. We'll talk about what noises owls make and then get very confused about what noises do foxes make. We still haven't figured that out. But then I will drop her off to her preschool and I'll go into work and I'll have a group meeting. And so I have a group, a research group. And so that's composed of lots of students doing their undergraduate degrees in astronomy. I also have grad students, just like Gail. Gail is not in my group. We should talk more, Gail. What you're doing sounds fantastic. And I also have what are called postdocs. So these are people who have become PhDs. They are experts in their field. And now they're doing research. 100% of the time, they're doing lots of research. So we get together and we discuss their latest results. We might read scientific papers. We might present to each other if we're going to be giving a talk. And it's really good fun. This is like a joy in my life because they're really smart people. And because I get to decide who gets into my research group, they're all really nice people. So it's nice. Surrounding myself with really smart, nice people is really great. Afterwards, I will get a coffee with some of my fellow professors. And then I am on an exam committee. So I am the big scary person examining a graduate student who's moving ahead with a project. And her project is super cool. So she's going to do really well, even though she's going to be really nervous. And that will go on for 2 hours. And then I get to research for the rest of the day. So that means checking in on my simulations, reading different new scientific works, and there's always new stuff coming out. There's like a weird comet coming into the inner solar system. Don't know if you've heard about it. A really big comet that everybody's very excited about. So I want to sit down and read what's going on there. And there's also so much other cool science. You know, if like two supermassive black holes find each other and merge, they can have a kick in one direction and fly out of the galaxy. So that's another thing I have to read about. So yeah, it's really nice. And there's lots of committee work and things like that. There's a running of a university, blah, 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 blah. But it's a really fun job. It doesn't even seem like a job sometimes if you phrase it like this. I'm just walking around reading and talking to people all day. But that's what it looks like. Observer, I'm a theorist, so I work with the mathematics and computer simulations. If you're an observer, it might look a little different. You might actually physically go to a telescope and be there and look at the sky with your amazing cameras. And yeah, so depending on what you actually work on, it might look different. Mine is particular for theorists.
At this point, I want Anne-Marie's job. How many of the rest of you want to do what Anne-Marie does? Because I know I would trade jobs with her right now, for sure.
And the owls at 6 a.m. It's
yes, the owls and the foxes. Yes.
Thank you everyone so much for your questions, and thank you so much, Dr. Madigan, for all of your answers and your absolutely incredible talk. I would also like to just introduce two following announcements that are coming up in Pretty Brainy as well. So we'd like to invite you to join us on October 19th for Ada Lovelace Day, which is our salute to the first computer programmer, Ada Lovelace. She wrote her first program 100 years before the computer was even built. And we're going to have a program also on how real success is about failing and bouncing back. So I'm going to put a chat in the URL right after this for where to register. And then secondly, I'd also like to extend the invite for November 2nd for another She Has the Floor, when Olivia Kuhn takes on the floor to talk about how to experiment with the amazing chemistry of outer space. So thank you so much again, Dr. Madigan, and I'm going to pass it back to Heidi.
Everybody, let's give big sparkles to Anne-Marie for today. And
Thank you very much.
For being here. Thank you to Gail for doing such important work with JEDI and helping to bring together JILA and Pretty Brainy, and to Kenna for that spark to get everything going. And finally, to every single one of you. So give each other big sparkles for being here and helping us kick off this fabulous series. And you start your days off tomorrow at 6 a.m. and maybe going out tonight before you go to bed and looking at the night sky and doing some observation. See what you can observe and see how fascinating it is, and then go to school and tell others about it tomorrow. All right. We hope to see you October 19 for Ada Lovelace, and again, November 2nd. Thank you, everyone. Bye.
Thank you.